degree, so it's a very good material for
उल्टा
agriculture
देवायला
applications. And
उल्टा
density
देवायला
is
उल्टा
2.21 grams per centimeter square, and
ठीक
then
है
that is
निम्मेट
very
वेली
close to that of the silicon. And then
निम्मेट
crystalline SiO2
निम्मेट
is
का करते
quartz that you probably know. Then atomic density, refractive index is 1.46. That was actually very good. Dielectric constant of silicon dioxide is 3.9. And then excellent electrical insulator. So resistivity is greater than 10 to 20 ohms per centimeter, and very high breakdown rate. That's why the silicon dioxide was there compared to the germanium oxide. Germanium oxide, that's why germanium was a better material. Initial transistor was with German, but it was all thrown out and replaced silicon. Now we have taken over completely. So the oxide structure, as I mentioned before, you have the oxygen atoms come in. This is the silicon substrate. Oxygen atoms comes in and forms the oxide with it. But there were some unsatisfied at the interface. Some silicon atoms have the dangling bonds. And these are actually the culprits that we say that hydrogen actually plays a role to participate. And then many different ways actually it forms oxide because the amorphous nature. So that's what of things this structure is. Now, how it is formed? There are several different type of oxidation process. Weight oxidation or the steam oxidation. That is actually you form, you send water vapors and you form oxide, and that actually is not extremely high quality. There is a is around 1200 degrees, 900 degrees to 1200 degrees. You can do that actual oxygen is then like faster than dry oxidation. Only advantage is a little bit faster, but the quality of oxide is not good. Then we have dry oxide, which is very thin. Typically, this thing actually goes to now is almost 1.2 to 1.5 nanometer. Some of the transistors in even 42 nanometer technology were using silicon oxynitride of 1.2 nanometers. And then this is actually dry oxide and wet oxide, and then room temperature silicon. In silicon, they have something called the native oxide. If you expose a clean silicon wafer to atmosphere, this was outside, it forms an oxide, which is close to 1 nanometer. So that is very 1.1 to 2 nanometer the oxide oxidation can be formed. So what people do actually is keep the wafer inside vacuum. Always stays inside the vacuum to grow the oxides or IK or. And then there is a volume expansion business. So silicon actually is, if you grow this oxide on the top of silicon, it consumes the silicon from the wafer. So this is the original surface. If you have a certain thickness of oxide grown, it consumes the silicon around 0.46% of silicon is used to grow actually 100% of oxide. So that actually is the typical formation of oxide. So this is very good quality. But imagine that if you leave oxygen very close to silicon, then you have an oxide. So if you deposit high K, let's say hafnium oxide on top of silicon, you will have automatically an interfacial layer of silicon dioxide. So that is actually the biggest problem. That's why that oxide quality is very difficult to control, the interfacial layer. So what people do is make sure that you have a good oxide to start with, so that it will block any further growth of oxide. And if you increase the temperature of the oxidation process, it increases. So people deposit in high K materials on the top of the good quality thin oxide, something like low temperature, 200 to 250. So the equipment, these are some of the processes, very important processes. You first actually clean the wafer, something called ASEA clean. Are you familiar with ASEA clean? Yeah, ASEA clean is a very standard one to remove all the ions from the surface. If there are some ions like sodium ions, they will go up. And then you start with this, and So typical process, you load this in a boat and then put it inside the furnace so you can actually heat the quartz structures. So this is actually the fabrication process of oxide. Now, how much oxide was grown? How to know these things? Very interesting thing is up to around 3 nanometers, you can actually know the exact oxide thickness looking at the color of these things because of the light reflection oxide thickness or to you can actually know the thickness or I can tell the color difference between the two films. I remember when we were doing 3 nanometers of oxide, you can actually see that it's 3 nanometers. If oxide thickness is higher, you can actually see. The best one is ellipsometer, which is extremely accurate. You can do that. We have in the lab several ellipsometers, actually 2 or 3 of them we have. So we can actually put some laser and then you can know exactly the thickness of the oxide. And that is the standard process. Even for high K, we do that. Now, what happens in the oxide? If you go to the MOS capacitor, which you are all familiar with, so this is typical MOS measurement. You have an AC voltage is applied on the top of the DC voltage. So like AC signal is superimposed. And then you start with this is the gate, metal gate or whatever this. And then you have oxide and you have the substrate. Now this is N-type silicon. So you start with first when your voltage is positive, the accumulation is takes place. These electrons are accumulated here. So you have this oxide. This is the CO is the oxide. Then when you start decreasing the voltage, going to a slowly negative, then the electrons are depleted. So you have a depletion region, and depletion region capacitance goes in series with the oxide capacitance. That's why these oxide capacitance starts going down, and the total capacitance. And then when you have this is because these positive charge here is mainly because of the ionized impurities. So similar to that of the P and Johnson depletion region, you have ionized impurities there, so they will be all positively charged. Once you have the potential, like electrons are gone. Electrons are this is N-type. Electrons are depleted. When electrons are depleted, what is for N-type? What is the typical dopant for N-type? Phosphorus or arsenic. And then these actually what they do is once the electrons are gone, the ions that are sitting there, they will be all positively charged. So they are, let's not here this positive charge. And then once you have the holes will be attracted there to form the channel, then the capacitance goes down and also becomes flat. So this is the typical process for software N-type. Accumulation is the positive gate voltage attract electrons. This is actually simple stuff. And depletion negative gate bias pushes electrons away, so you have no charge at the interface. Or these the ionized impurities will be there. And then the inverse of this become negative, and then it becomes flat. Why it doesn't go back? That actually we'll discuss now. But this is typical the process of MOS. This high frequency MOS characteristics. This is the band diagram. If you look at, if you have a bands, normally assume the bands are flat to start with. Now, when you do the accumulation, this is this is P-type semiconductor. If you do accumulations, then what happens in accumulation? In P-type semiconductor, a lot of holes come in. So that's why there is a band bending. And the holes, this conduction band is going very close to the formula when the holes are at the interface. Typically, if you look at these ones, so Q phi F is actually the measure of number of impurity atoms in the substrate. depending on the impurity atoms, let's say these impurity atoms are moderately like N doped, P doped, then P doped, the Fermi level is below the intrinsic Fermi level. For N doped, the Fermi level will be above the intrinsic Fermi level. Since this is P type, you have those things below the Fermi level. Depending on the number of atoms or the number of impurity atoms, you have those this separation will be. Now, if you look at an intrinsic silicon, where there is no impurity at all, the Fermi level stays exactly at the middle. What is Fermi level? Fermi level is just a statistical distribution of electrons inside the electron. So now, when you accumulation, because you have more holes, so this is actually represents at the surface only, initially at the interface. You have it's very close to the conduction valence band. Now, when you do the depletion, now the band bends other way, and in depletion, it actually goes. That means you have at the interface, the holes are depleted. Once the holes are depleted, the Fermi level actually goes close to the intrinsic one. Then, when you go for inversion, the Fermi level actually crosses the intrinsic one, so that representing there is electrons at the intrinsic and during the inversion. This is the P type. Any questions in this one? You're all familiar with this one? Now, if you look at what is the impact of frequency, if you look at the impact of frequency, and if you look at first the holes, this is your accumulation. This is one goes this way, and if you go this one, is that what is the difference there? Why this way and why that? P type and N type. So the frequency, if you do that extremely low frequency measurements, then you see this capacitance which in the accumulation and also inversion in the low frequency goes back up. But if you do high frequency, it actually becomes flat. That's because the minority charge that you have, generation at the interface can follow the AC signal. What is the minority charge in this? This is electrons. To go for a low frequency, they are actually pulled from the substrate. That's why they follow the low frequency. Actually, they follow the AC signal. That's why you see the C inversion will be similar to Cox. This is actually Cox. And now this is the combination of the Cox and CD, the depletion capacitance. Now in high frequency, this is actually becomes, so you cannot follow the generation of carriers that is coming from the substrate, cannot follow the high frequency. That's why this capacitance doesn't change. And then if you go to deep depletion, so if you go for high scanning speed, or you increase the speed of measurement, then this goes to deep depletion. That means the depletion width starts increasing, because it will not be able to track the carriers coming in. So it will look like as if the depletion region is increasing. That's why the capacitance will continuously go down because of this combination issue. This is the CSI, is the depletion capacitance. Now this is increased to balance the gate charge. So this is XD, that in the depletion region will expand. That will be happening. But once the inversion takes place, the depletion region remains constant. So it doesn't change. So this is actually this is the depletion region with XD, and this is depending on the doping, it directly relates to it. This is the basic principle. So why we do all these measurements? The idea is to see if you have an ideal curve. This is your flat band. The flat band is before, as I mentioned, this characteristic. This is actually we make the bands flat before applying any potentials. But bands are actually not flat to start with. They are because of the work function difference from the metal to substrate, and also the charge in the side, the QSS. whatever that thing. So that's flat band has two components. One is IMS, the metal to semiconductor or semiconductors, and the QSS over COX is a potential that is responsible for the because of the charge oxide, fixed oxide charge. So this is so that actually the oxides. Okay. Next one is what is its impact on the interface? Why we do this measurement? If this is our flat band, if there is a charge distribute change, let's say you have fixed oxide charge, you take it these things, whatever fixed oxide charge, whatever get metal doesn't change. But if the charge in the interface changes, or charge in the bulk changes, there is a shift in this curve, where it will shift this way, or it will shift that, depending on the positive charge. That's why it is very important to people follow the capacitance measurement. Even for all applications, there is a capacitance measurement. They can know exactly how much is planted. And another thing also from here, you can actually know if you know the area of the get material, get metal, then you can know exactly what is the doping. You can calculate the doping. You can calculate the dielectric constant, because you know the oxide exact capacitance value. So if you know the area, you can know the dielectric constant. That means if your oxide quality is not very good, then your dielectric constant will not be 3.9. They can change from 3.2 to whatever this is. And now if you have both silicon dioxide and high K, then you have a combination of this. So that's why we get the ULT. If we know the thickness, we don't know the dielectric constant, but we know the capacitance and area, we can always find out what is the thickness. Okay, what impacts, first of all, the type of dielectric? If you have silicon dioxide, silicon oxide, nitride, and high K, it actually this also impacts the interface and the charge in the interface. And the substrate, if you change the substrate to silicon germanium or 3,5, that also will modify the interface charge and the CV measurements. It will not be the same for every battery. And then, just in case you have process conditions and thermal budget, if you anneal the sample in a different condition, or in nitrogen, it will be a different one. If you anneal the sample in oxygen, it will be a different CV curves. So, and then obviously defines operating conditions. First of all, the temperature. What temperature you are operating this? So that will be a different value. And also, if you do the electrical stress, we'll discuss some of those. Then also it will change. Even the devices, when you go through, it make an inverter, and then run the device several cycles, then you will see it will also shift. The flat band voltage will shift because the charge in the oxide changes. And of course, it is very small, so that's why we have the chips sitting there for at least 5 years. All designs, when you make the device, all the circuits, the reliability requirement is these circuits or the device should work for 10 years. And after 10 years, of course, that is the minimum requirement. Sometimes they can work different. Now, interface charge and interface state density. What is actually these results of a structural imperfection that exists at the interface no matter what you do. So that creates some of the interface state density or interface charge. The interface states, or you can say interface trap, also release electron and generate noise. These guys are actually very crucial. So that has been studied, the interface state density has been studied for a long time. And now with the high K, and also it is very important because the amount of charge that we are going to manage inside the device is so small. If its interface charge will be higher, then it will be and also degrades the surface hold current in the MOSFET. And more interface states and fixed charge appear after the oxides. If you give this high electric field stress, then the interface state density changes. We will see how it works. And obviously, there is bond breaking in the interface. and the rearrangement of chemical bonds, because when you have this type of thing, let's say if you stress the device in high voltage, and then it will break some of the bonds. Now you leave it in the room temperature for some time, then some of the repairing also will take place because of the room temperature itself will fix some of the bonds. So it will break and repairs, that sort of things also. And the threshold voltage and transistor current will change because with the use and potential cause the sensitive circuit failure. So if you have changes, if you encounter changes on these things, some of this this happened actually in NEC some time ago. They delivered some computers, but one or two computers failed very quickly, and they took them back and looked at that thing, because what happened during the fabrication process, they exposed to some environment. The oxide itself was the age of the oxide, which normally we design for 10 years, as I mentioned. It was already aged almost dead. So it was supposed to live for 10 years. It's already 9.5 years old. So in 2 months they died. So this is actually was a serious problem. So sometime to understand that every process, several ways they modify and understand that thing in the beginning. And then obviously it degrades the channel mobility and transconductance. So this is actually very serious one. What actually is the interface type defects? If you have interface type defects, and they distribute in the energy band gap of silicon, and these ones, there are different states. You have donor states and you have acceptor states. So they are capturing electrons, and donor states actually can give them, that means they capture holes. So this is, and then obviously with the potential, these defect sites will also change their characteristics. That we saw this band diagram. So what is that? Yesterday there was a question on formula-level pinning. What is actually formula-level pinning? If you have large density of interface states, then before even you have any potential applied, these states capture electrons. When they capture electrons, from where do they capture electrons? There's several sources. First of all, they can capture electrons from the transition band or from the impurities next to them. Impurities actually around this area. So once the impurities are attracted, then that means this site you have some of the fixed charge because of the ionized impurities. And then this area, which is, we have some of these levels, these are actually the neutral level. And this area, if you have large density of these things, then if you look at the total charge at the interface, the QIT, let's say, this is similar to the QD. That means that there is a depletion layer is formed, which is ND and WD. And that depends on the formula-level difference there. This formula-level difference, EF minus E0. Let's say this is the E0, the red line. And then that will decrease, this formula-level difference is decreased because this is a fixed amount. And if DIT or the interface defects are very large, or typically mathematically it should be infinite, that means very large, then the formula will actually sort of fall the pin to the B0 level. After that, if you apply the voltage, then you don't see any band bending, so nothing happens. So that's why it is the device, that's what we call the formula level pin. And then you don't have any changes because of the potential applied from there. Typically, potential when you have additional band bending, all sort of things for the device application, but that doesn't work. So this is a serious issue. The idea is to reduce the number of interface defects. So if the density of band gap states near 50, which is here, is very large, then addition or depletion of electrons to semiconductor doesn't alter the formula level position at the surface, and formula level is set to be. And then you are stuck with it, and that's where the device is. So what is the silicon dioxide interface looks like? You have different planes, as I mentioned, the density of defects at different planes. So if you look at silicon 100, 111 plane, you have something called the PV center, or the simple dangling bonds. And the energy distribution of in 100 they have PV0 and PV1, two different types. They are called actually the defects that has been identified. And the energy distribution of this 111 plane is somehow this is the TIT and this is the band gap energy. So they will follow something like this. And for the 100 plane, they follow a slightly different energy distribution. And from these actually, and also ESR measurement, the electronic spin resonance measurement, they found out that they have actually two different types of 100. And identifying these defects and their contribution to the device operation is a very challenging case. Because it is, if you go to change the material from silicon to silicon germanium or gallium arsenide, it is very difficult to identify these defects of the gallium bonds. And typical passivation for this is low temperature forming gas anneal. So you can just anneal with hydrogen. Forming gas is what is the percentage of hydrogen in forming gas? The idea is actually 90% nitrogen and 10% hydrogen. And that is good enough to passivate all the dangling bonds in the surface. If the dangling bonds are sort of PV0 type, or PV1, it is also very difficult to passivate. So even with hydrogen annealing, you do not have all the interface states passivate. Now, how to characterize this? One thing that we say that one is the low frequency CV and high frequency CV. And these are some indirect techniques. You can measure this high frequency and low frequency measurement and calculate the DIT. There is a direct technique called the conductance measurement. But if you have large gate leakage, let's say the oxide quality is not very good, leakage is large, then both these measurements will have problem. Problem in the sense the accuracy of that one. And then there is a measurement technique called deep level transient spectroscopy. That also DLTS, that also works a little bit. People use DLTS measurement to estimate the. And in MOS transistor, there is a weak inversion. 1/f noise is also used to calculate because 1/f noise is directly related to the defects very close to the interface. And then there is a current DLTS, and typically DLTS is the capacitance transient. If you can do the current transient measurements by pulses, you can also do that. And DCIV measurement, you can change the temperature of the current voltage measurements. And also charge pumping measurements. So you can do charge pumping measurements in a transistor. So the MOS capacitor characterization, again, coming back to this, there is a model actually. There are several ways you can characterize this. One is you have the dielectric capacitance of the gate capacitance or oxide capacitance. Then you have the depletion region capacitance. And then comes you have IT capacitance, which is parallel to the depletion capacitance, is the interface state capacitance. And that is in series with the resistance, series resistance. So then you can go for simplified model, convert this one to the conductance, and then you can just go for the conductance, and then everything will be conductance and capacitance. So you can get the result. So typically, if you do, as I mentioned about the flat band voltage strip, if you no defects are present, like the ideal device, you have the CV characteristics looks like this is high frequency and this is a low frequency CV. But if you have defects present, then it's 6. And then in the measurement also, you can have low frequency and high frequency. There is a slight difference there. And that is because of the series resistance method, the series resistance, impact of series resistance. So to get this accuracy, this measurement, you may have to correct the series resistance effect. So that's what the typical is done. And then you calculate the total capacitance, you calculate that way. And then the interface state density, you calculate also from the low frequency measurement and high frequency measurement and the total dielectric capacitance. That can give you, from this measurement, you can actually estimate the interface state density. Another method is the conductance method, as I mentioned. If you measure the same device conductance as a function of frequency, then you have a peak and with for different gate biases. So whatever the highest peak, from there you can also measure the interface state density. And then this is GPO, or the conductance over the omega, and that will actually give this. This is the expression for these constants. So you can measure, and once you have the measured data, then you can do the quantum mechanical corrections. What is quantum mechanical correction that we discussed that thing? It is a slight variation of the measurement system that we do. The charge that we measure through these machines is slightly different if you look at in the classical method and quantum mechanical. Our measurement system with standard equipment is classical. So there is a small variation. So you can shift each values a little bit by modifying the quantum mechanical impact. There is a slight delta change you can make in sugar data. I think that is available in the North Carolina State University on the websites to download and software to modify the simple measurements. And then if you look at, this is the DIT measurement. This is from the Schroeder's book. And what it does actually, it is, you can see the 10111 plane, there are two different measurements. One is the conductance method and one is quasi-static. This case actually the leakage current through the dielectric is extremely low because the thickness is a little bit high. So that's why you can see the conductance measurements matches very well with that of the quasi-static. Quasi-static measurement is the bullets and the conductance is the rectangular cross. Whereas this is actually the distribution of 100. You can see this measurement is like this, and this is the conductance measurement also follows similar way. Even though you may not be able to calculate the entire profile, but you can know some of these things in the energy cap. What is the energy level of those defects and how they being distributed. This is the typical distribution of. Any questions now on the interface states? And those are still present in IK. They are still present in FinFETs. They are present in the smallest possible device. You still have interface states. No questions? So what we did actually, this is a DLTS measurement interface traps. We had some took the silicon wafer and exposed to the inert plasma, yes, argon plasma and so on things, and remove one monolayer of silicon, and then took the measurement through the DLTS. And first of all, in the CV measurement, you can see a very large flat band voltage shift. If you do this simple weight etching, like this, just cleaning, and then you expose to 800 volts reactive ionizing system or the plasma etching, then you see there is a lot of difference created at the interface. And that even can also measure through DLTS by giving pulse to the interface, by filling up all the interface defects. Typically, I will explain the DLTS measurement system a little bit later. But what you do, you give a pulse, so you fill up all the interface with electrons and take them away. Just take the pulse out. So what it actually does now, while you're doing that continuously, you also change the temperature. When you go to very low temperature, those who are room temperature, those electrons are filling up and leaving because the room temperature is good enough for them to be emitted. In low temperature, they are stuck because the time constant is high. So depending on your frequency of pulsing, you can exactly know the where in the band gap they sit. This particular case, they are actually 0.57 electron volts from the conduction band to the trap band. And this is in the silicon, but from conduction band below exactly is 0.57 electron volts. So that is actually in the deep level. There are two different levels. One is the shallow level, one is deep level. Shallow level is less than 0.1. Anything less than 0.1 is shallow level. But once you go to 0.3 or 0.4 or 0.2, they are sort of deep level. So the other measurement is charge pumping measurement. Charge pumping actually is a very stable and very good measurement system that is actually can be done with the pulse generator and the transistor measurement. So it measures the interface density at the substrate and gate oxide interface in a transistor. So resolution is very low, 9 states or better, and also sometimes it can identify a single track, and it determines the separate shifts in threshold and flat band voltages from the interface transistor. So you can see how the shift is taking place there, and the also determines the energy distribution in the interface states and give information of the spatial distribution. Let's say if you have a large MOS transistor with a gate area is large, like gate length and gate length and width, you can see how they are distributed from the source to drain. What are the defect level? What are the defect concentration is very high. Because of this, you can actually take some hot electron effect and check whether the hot electron effect is creating additional defects in the drain. And then measure the inversion charge density, and in high K with thin interface layer measure the density of bulk high K states. That means if you do a thin silicon dioxide and deposit high K, by adjusting the frequency of measurement, you can actually look at from the interface towards the high K. So people actually use the charge pumping to look at the silicon dioxide and high K interface. Because if you have silicon dioxide and there is high K, that is also a different interface. So is that contributing something? Is that contributing the defects of the charge to the device? So typical setup for charge pumping is this: if you have, you can reverse bias the source and drain, and this connect them together, and then you give a pulse to the gate, and then measure the drain, apply the gate pulse and measure the substrate current, and see how the substrate current is varying. So you start with go above the threshold voltage and also below the flat band. That's sort of the pulse height you have to decide. And the pulse width actually is different. Pulse width actually changes the frequency, how fast you want to contract, or you can change as a function of different frequencies so that you can know the concentration of the frequency. And then this is another example in the CV measurements. This is actually again on plasma damage exposure to plasma etching. And if you look at the CV measurement just immediately after completion of the device, then you can see how the distribution. This is actually a weighted device, but once you have the plasma etch, they actually go back. These are the different weight clean, and then you have different type of plasma exposure. Let's say SF6 plus O2, SF6 different plasmas, and then followed by a forming gas anneal. And once you have forming gas anneal, after annealing, a lot of this plasma voltage shift here is gone. And then obviously these devices actually get spread at the low frequency level. So what he says is that actually if you do the forming gas anneal, definitely hydrogen contributes to the interface and makes the interface very bad. Questions? We can discuss. There is nothing to big deal.
These are all practical data.
Yeah, these are all experimental measurements. We did it in the lab. So this doesn't take very fancy equipment. If you have a CV meter, and if you have and then the pulse generator, then you can start creating this. Yes.
How to then the CV measurement for most capacitance of using KF as a direct equipment. Yeah. And I found that there is a shifting in the accumulation region. As I increase the frequency from 500 to 1 megahertz, then 1 megahertz to 2 megahertz, there is shifting in the accumulation region.
The COX, that means COX distance.
Yes. So what might be the?
So this is actually because of the frequency variation. That is because there is a seed resistance. That seed resistance I calculated, I mentioned that if the seed resistance is extremely high, you see once you change the frequency, the capacitance itself will change, the accumulation capacitance will change.
That is due to the set resistance.
Yeah, that's due to set resistance. So you can see that there is a variation of the accumulation capacitance as a function of frequency. That is called the frequency dispersion. So that is very standard if you have set resistance. Okay. Because especially when you have very sensitive device and even the set resistance comes from the leakage current. Measure the leakage current. The best way to know that if you have a different leakage current, then it's the best way. Those who have low leakage current, you will see that the change as a function of frequency, accumulation capacitance will be much less. For large leakage current, then you can see that is, the change will be large. Have you tried anything like that?
It is going.
Because leakage current changes your CV measurement. It has a lot of impact. The best way to have a thick one, which your leakage current is low. Then you see in that one you can actually check. And then you increase the leakage current by stressing this. Then we will be creating a lot of defects in there. Once you stress and defects are more, then leakage current goes up. Then you see the shift again.
And one more thing. And for this contact, aluminum contact. So is there any effect of it while making the contact at the interface between the dielectric and the metal contact?
Typically, if you make aluminum contacts, should not be much difference. But if you do not anneal, just after depositing aluminum, what happens? There is a barrier it forms. So then your accuracy of measurement goes down. Because aluminum, the barrier height is how much? 1 point something. Because it's like a Schottky barrier to silicon. Okay. And also the changes with the doping. And you cannot do in those devices, you cannot do N plus doping. You have to moderately doped about the substrate. What is your substrate? Just metal? P-type silicon substrate. So if this is P plus, you will see the contact is not a problem. But if you have, see normally those who want to have very good capacitors, they make a P substrate, and at the end they make a P plus, then make a contact. Like in the substrate. So let's say you have in the back side, you're making a contact in the back side. Can you make a little bit of P plus there? If not, then you put deposit aluminum and anneal it.
The back side of the silicon substrate.
But backside of the silicon substrate. Otherwise, it will form a barrier to aluminum to silicon barrier, and that will also create error. So, sometimes people use also the contact. If you're using a measurement and just putting the sample in on gravity on a chuck, which is one of the contacts, the backside contact, that is also not very good. That also will create additional resistance there. So best thing is you can use some silver paint and hold these samples on the substrate with vacuum. That means it will suck substrate without making a good contact with the substrate, with the chuck.
So without making without depositing the contact on the backside, we can use that one state propagation.
No, that will not work very well also. What I'm saying is if you have a backside contact and you put that on the top of this chuck on gravity, which is just sitting there, and your probe is on the top, then also in addition to gravity, you have to have a better contact. If you don't have vacuum, then the idea is to have some silver paint so that you can make good contact with the substrate. So these are small little experimental things also there. And plus your cables, watch your cables. And if your CV meter is there, you make sure the initial value before any contacts is 0. Many CV meters will allow to adjust the parameters for the cables to reduce the capacity. Because cables sometimes can add a lot of capacities. And they will change with your voltage. And this is actually the same CV plots. When we calculate these before annealing and after annealing, you can see the distribution of interface state density. That actually you can calculate from the frequency values. Any other question? Another thing also, we did measurement. If you, we took some wafers, were processed and make some metal etching on the wafer and created devices across a large 8-inch wafer. This is actually many devices around this. So we measured some of the initial electron trapping slopes. What you do is just give a small current to the dielectric, then you see how it changes. These are actually transistors. And we stress the transistors, and they then follow how the leakage current changes. The initial stress, when you follow that, there is a current slope. You can calculate from there. Just a simple experiment. Calculate the current slope. If you have a wafer like this, 8-inch wafer and different locations, we took some measurement. These values will be exactly identical. But we found out that there is a different thing actually. There is a one is one side outside this ring is gate injection mode during the fabrication itself, and then in the middle it was substrate injection. Substrate injection means during the plasma processing, you can see because of the charge neutrality balance, sometimes the electrons can be injected from the substrate to the gate or from gate to substrate. So that actually completely changes the characteristics. So this is actually happens. Now this is sort of the distribution because of the substrate potential changes. You can see this there is a low point in here around this. It's the lowest point, and then suddenly it increases outwards, and then also increases. So that actually, then once we have these measurements, then we looked at why this is happening. Now, if we inject from one side, the side that you are injecting the electrons, that is called the cathode. The other side is anode. So typically, if we inject electrons from this side to that side, so the cathode is this side. So the maximum charge distribution remains towards the cathode side. So when the electrons are injected from the gate, hot holes, then this is actually a typical case. Electrons are injected, there are some holes, electron hole pairs are generated. The hot holes will go through, travel through this dielectric and create the defects, maximum defects actually to the injection side. So that's what actually, if you calculate from the, as a function of the distance here, you can see this distribution. So based on that, actually, for the substrate injection, traps are formed in the silicon dioxide interface. For gate injection, whereas this will be at the gate silicon dioxide interface. That actually you can find. And then you can look at this electron trapping slope, which is actually a measure of the plasma charging damage. And then look at, subject to these devices, to this change in threshold voltage. So we measured after that threshold voltage variations. Those devices were subject to the gate injection method. They were actually not very significantly impacted, whereas there is a large impact in the substrate injection. The substrate injection, the defects were created very close to the interface, and then you have large change in threshold voltage, change the charge variations. The charge that was created close to the gate interface, that actually was not very significant. And that also we found out the hot carrier measurement we did. And then look at what actually how it is changing as a function of substrate injection and gate injection. In gate injection also we saw that there is some hot carrier degradation, but then again after that it's become saturated once we have the trapping slope changes. So there are many different ways you can actually extract depending on your device and the transistor, depending on what. See, we didn't know that. For this device, we didn't know what exactly was happening. But typically, when you are doing a wafer processing, it's possible there is the ring formation inside because of the plasma. All the majority of the processing now we're using plasma and LED processes to pattern the different structures, to pattern the gate. Everything is all dry etching. So this one actually a very interesting result when I was in the labs. I was in my sabbatical, so we give this experiment. Now, hot carrier effect, the hot carrier induced hydrogen depassivation actually is another issue. Now, when you normally when the transistor is done, you anneal with a forming gas. It is not supply enough hydrogen so that it passivates all the diamine. But just in case the device operates, when device operates, let's say the inverter, when the inverter suddenly input becomes VDD, and that time actually the gate voltage is extremely low. So gate voltage was 1, and then this was at VDD. So when it was increasing, that time actually the device will face the drain side, a lot of damages that time. So that is a hot carrier damage. But that is a very minor thing, but how it is impacting that's whatever it is. So the hydrogen depassivation takes place if the energy of those carriers are very high. And then improvement after level was observed when the device was annealed by deuterium. So what people said actually, why not put deuterium on those places instead of hydrogen? So that we can, because it is very difficult the electron to knock off a deuterium ion other than a hydrogen ion. So that actually deuterium annealing started. And this is the first, the University of Urbana, they introduced this one. And we did some deuterium implantation cases into silicon substrate before the oxide was grown. So the deuterium goes to the interface and accumulates there. So this is actually depending on the implantation depth and the dose number of deuterium atoms, you can get the best results in the interface state density changes because of this deuterium. After this device is completed, you see the deuterium diffuses and goes to the interface. But if it is exposed to very high temperature, deuterium can out diffuse completely and then may not be left in the interface. So there are this is deuterium implantation cases. Another thing also to improve the interface is nitrogen incorporation. So this nitrogen was incorporated actually by annealing. Typically, you can anneal with 2 gas so that you can have some nitrogen goes to the interface. And we did one experiment with implant this. What you do, you implant nitrogen first to the silicon substrate, very low power and low dose implantation. Because you need only 10% of nitrogen into silicon dioxide. And then when you grow the oxide, the nitrogen gets into the oxide. And that is done, so improve the stress induced threshold voltage. What we did, this one again, if you look at the cumulative distribution of this, we have 2 different ones. One is the simple oxide characteristics in the before and the nitrogen implanted ones. Both of them showed similar results to start with. But once you stress them, and then you see this, the simple ones actually shifted a large distribution. This is the hole trapping, because of the hole trapping or the defects with the carrier trapping. This shifted this failure, the threshold voltage shifted a lot. But whereas the nitrogen implanted, there is some shift, but it's much less. So those are some initial work we did, and then it was clear that we need, those days people were only using silicon dioxide. And it was clear that nitrogen has some impact. It was published in IDM and it was in DFC, devices as well. Then industry actually adopted the nitrogen oxynitride, silicon oxynitride came into that. And then is also this average GM, this is the transconductance variations. Actually, for control oxide, it's very large compared to the nitrogen implanted one. Okay, so what actually oxide degradation actually takes place? As I mentioned, if you have electrons, let's say this, electrons are injected from the gate, and then they go to the substrate, and they form electron hole pairs from the silicon. Then you have the either these holes or it knock off the hydrogen. The hydrogen diffuses back towards the gate. During this process, it creates a lot of defects or breaks the bonds. So that's what actually, so there are 2 types of defects created because of this process. So this is one thing is the hydrogen which was passivating the interface was gone. And the second thing also, this hydrogen creates a lot of defects inside the which is also true in high-K devices. We found exactly the same process. So it creates interface defects as well as bulk defects. Bulk in the sense those are inside the oxide defects. And that contributes to the additional charge trapping plus fixed oxide charge. So these are actually called the secondary damage. Sometimes also you get secondary damage depending on the hydrogen energy of this hydrogen that goes there. The field, mostly in the field. So this silicon dioxide interface is very well studied, and you have pretty good idea of it. And there's a very well studied interface, and we have introduced hydrogen, plutonium, nitrogen, everything at the interface to improve the data cycle. Nitrogen implantation was abundant because it gives some sort of damage, no matter how low the implantation is, it gives some sort of effects in the silicon substrate, and that is not acceptable. So, but the N2 anneal was the process to have silicon oxynitride. That was even today is being followed. Many of the, even in the most recent ones, for example, if you look at 14 nanometer technology, they have oxynitride. In addition to the high-K evidence. It's not that entire wafer, also the entire chip has all high-K. They have oxynitride where you need extremely high-speed transistors, you still use oxynitride. Even though that is the power consumption is very high there, but you need the power, the performance there. And then ultimately silicon oxynitride is introduced, and this is actually has been the trend even now. So now we'll go to silicon and high-K interface. As we discussed, we saw this one. Because the high-K was introduced because of this leakage simple direct only current. And it was not managed. And in the process, in the 45 nanometer, the first we started this high-K introduction, and also 22 nanometer is still high-K. And there was a process, silicon in the beginning, actually silicon oxynitride and then high-K. But that was not because you have silicon oxynitride, then the minimum thickness goes around 1.2 at 1.5 nanometers. So that is not acceptable. But then you have very thick, and you cannot scale the EOT below 1 nanometer. It would be something like 0.9 or 1 nanometer. So now these most recent devices you need around 0.5 to 0.7 nanometer EOT. So that's why this was not done, mostly done with the silicon dioxide. So this is interface layer and high reliability. So the charge trapping, we discussed this one before. We did some experimental measurement of this with a constant voltage stress. If you take these devices and give a constant voltage stress and then increase the potential, so let's say for a higher potential, you have large flat band voltage. And then the interesting thing is you can leave it over time and there will be some detrapping. So there's an initial volt detrap, let's say this is the initial structure. Then you move because of this flat band voltage shift. If you leave it over time, it will move back. So that actually because of the shallow traps. Or if you give a reverse potential, let's say if you started with the stress from gate to substrate and you change the substrate to gate, then a lot of these things actually move back. But it's very difficult sometimes, depending on the voltage level, you may not come back to the original place that I was saying because of the detrapping. If you have all the defects in the shallow level, then you have very good chance that you get detrapping. But we do not use the voltage level that low actually for simple performance. Let's say it's 0.18 micro technology, we are using 1.8 volts. Even threshold voltage, the VDD is very high. So that actually makes the shift sort of very small shifts every time the device works. So hole trapping actually you can do initially occurs near the substrate during the stress, and the electron trapping occurs near the gate. So that happens once we do this experiment. So the gradual extension of electron trapping towards the substrate offsets the hole trapping. That is one, and then detrapping changes the shift back. So this is actually the initial electron detrapping, so it moves back this way, the whole detrap moves back that way. And then the another thing also, the interfacial layer that you have silicon dioxide little bit layer that is there before. So that also contributes to breakdown. So details of the breakdown measurements we'll discuss in that. I think tomorrow we'll discuss this. So individual breakdown mechanism of this oxide actually depends. So we'll talk about it. And there is something called stress-induced leakage current also. As I mentioned before, that if you change the look at the stress, if you have defects created, the leakage current through the gate will change. Let's say there is a initial device freshly made, and then you take some measurement, whatever the leakage current through the gate, and now you stress it a little bit, and see, stress in the sense you apply a little, let's say the device is designed for 1.8 volts, then you can apply, let's say, 2 volts for maybe 1,000 seconds. Then that will be enough to create a lot of defects inside. Because you go beyond, the purity is a little higher than the 1.8 volt. So then once those defects are created, you see the leakage current will change. So and slowly leakage current will change and until the oxide breaks down. So we can see that thing a little bit more on the cell tomorrow when we discuss about the reliability and the cell properties. And then if you look at the leakage current again, so interesting thing actually, we did one experiment. Here we had the silicon dioxide, and that was the in situ grown silicon dioxide. Then we had high K layer. Now, to understand what contribution the interface layer is doing, it is very challenging to do that. Because unless you separate them, then you don't know who is contributing how much. So what we did actually, we did one gate stack, silicon dioxide and high K. And then we went only with the silicon dioxide, exactly the same way prepared. And then we went for another capacitor we made, exactly same thickness and same deposition process for high K, but we formed the metal and high K and metal capacitor. That's MIM capacitor, metal insulator and metal capacitor. So then we can compare how they behave. So this is actually the combined device which has silicon dioxide and high K. And when you stress, there is a change of different temperatures. We looked at different temperatures. And then see there is a evolution. They say with as a function of stress time, the current increased. And then we saw when you do only silicon dioxide, which is the interfacial layer. This is actually only silicon dioxide. This is the combined one. So this still shows a power law dependent in there. Power law in the sense I will discuss the NVTI issue tomorrow. When you stress these things, depending on the defect creation, the increase as a function of time, this is the N. So this is actually power of this N. That means it follows that. That means the defects is directly created. There is a lot of different models out there, so we'll talk about that. And then when you do the MIM capacitance, only this tin and 4 nanometer of hafnium oxide and tin, there is no actually change in both temperatures. You can see there is no change. So this thermally activated in this case, only the magnitude change. As a function of time, it did change. Then when you combine this one, then you can see that this is the hafnium oxide as well as the interfacial layer. Then you can see the similar behavior. So that means the actual culprit in this case is the interfacial layer. Interfacial layer contribution that was identified. Sort of we are the first to report that even though people knew, because the dielectric constant of silicon dioxide is smaller than the high K layer, then if you have a gate stack and apply some voltage, so the material where the dielectric constant is low, the voltage across that is much higher. Let's say if I apply 10 volts across this, you can get 8 volts across that thin oxide and maybe 2 volts across the high K, because the dielectric constant is different. So the field across this, the high K is much higher. that was actually reported. But it is directly a direct evidence of the breakdown and the defect generation in the silicon interfacial layer, silicon dioxide interfacial layer we reported first. That actually is the weak link in this process. And then if you look at the breakdown, we'll go through the breakdown process more detail tomorrow. But when you break down, actually what happens, you measure the leakage current in a stop and measure. First of all, the defect generation and charge traffic, this will start going down. And then this peaks actually starts with the soft breakdown. And then suddenly it becomes the hard breakdown. That is actually the process that is breakdown process follows. And if you use the only silicon dioxide, then you can see this also changes that way. But in the MIM capacitors, there is no change in the trapping size, no soft breakdown. It goes all the way to hard breakdown. So this work actually we reported first that look, this interfacial layer, and we changed this interfacial layer to many different types, like whether it's ozone treated interfacial layer or it is intentionally grown thermal oxide, thermal silicon dioxide. All cases, the silicon dioxide was the culprit to entire gate stack. And then we looked at this process again, the defect distribution by the charge pumping method that I mentioned. If you change the frequency, what happens is if you look at the leakage current through this and the changing the frequency from 1 kilohertz to 1 megahertz pulse frequency, then you can know how the distribution of defects inside the oxide all the way to the interfacial layer and high K layer. That actually you can actually measure with the charge pump. So that defect generation rate is, even though defect generation is constant in the oxide. So, okay, now oxide is the culprit. Now, how do you know how the defects are formed inside the oxide? That is what you also understand. And then we looked at that thing, whether at the interface there are more defects, or at the high K and silicon dioxide interface more defects, or high silicon dioxide or silicon substrate interface more defects. That is another thing everybody was interested to know. This one experiment actually showed that actually the defect distribution across the little silicon dioxide is large. But once it reaches the high K interface, then suddenly the defect distribution is just taking hard. Then we looked at, this is the mobility degradation. Many people reported that one. And the high K, because of the fixed charge and phase separation crystallization. Remember yesterday I mentioned it's possible that inside the high K layer there may be some nanocrystals will be present. The crystalline hafnium oxide will be there. Hafnium oxide crystallizes around 800 degrees centigrade. So 750 or something small microcrystals will start to form inside the hafnium oxide. But we need for our MOS applications, CMOS applications, we need this oxides to be completely anonymous. Then we get better quality insulation. So this actually, if you have phase crystallization, then you have mobility degrades very badly. This is silicon dioxide, and this is the universal core. But if we use high K and silicon dioxide, then mobility degrades very badly. And then found out what was the reason for that. And then you can go for this is electron mobility and hole mobility. So this is actually in the beginning. I'm talking about 2003 and 2004. Around that time, it was very serious issue to integrate high K talent. So from 2004 to 2007, there was a lot of extensive work. And 2007 was the first time they introduced high K. Even Intel, when Intel introduced, IBM was unable to introduce that time. And then obviously AMD, they are also manufacturing those days, they were manufacturing the microprocessor, they were having trouble also. And then when Intel introduced, almost everybody looked at the composition of that high K material and interfacial. They bought the Pentium chip and etched all the way to the transistor. And look at the SIMs and different physical characteristics to identify the atoms there. So this is the mobility degradation part. Then various dielectric also new LD process. I will give some ideas. We will go into much more. I think I mentioned about the cycles. You deposit few cycles and then you expose to plasma or deposit few cycles. To just get 2 nanometer of oxide, you may have around 40 cycles. So every 10 cycles, you stop and expose to plasma or anneal also that whatever films you have already deposited. Then go to the next 10 cycles and then complete 40 cycles to get to 3 nanometer IK. That is actually DAD, as I said, as deposited is a standard deposition process. Like you deposit all through continuously 40 cycles. Or you can go for 10 cycles and dielectric deposition and then thermal annealing. Then you go for 10 more cycles and annealing. So that is called deposition, annealing, deposition, annealing. Another one is dielectric deposition and exposed to argon plasma. Then deposition and S is for plasma exposure. And deposition plasma exposure like this, you go for 40 cycles. Every 10 cycles or 15 cycles, you can change and stop and expose to that. That is DST. If you look at the interface, changes because of that. So this as deposited has a little bit higher interface density in the band gap, whereas the DSDS has the lowest one, because that actually densifies the film and reduces some of the interface. So we also have to look at what contributes to this reduction. It doesn't look much difference, but it is device grade is very significant. Whereas the DAD was a little bit worse in terms of the annealing didn't help, but plasma exposure did reduce the interface density. And then if you go for the mid gap interface density, you can see also DSDS. If you change the interfacial layer, instead of the silicon dioxide, you go for the silicon oxynitride. You change the this KMOX or this RFN is with a chlorine nitridation. That way. If you do that, or you can go for SPON. That is SPA is the slot plane plasma antenna plasma slot plane antenna plasma, and with nitridation. You change the interface, your DIT or the interface density also will change. So anytime you make a device, it doesn't matter how you make it, as long as you have it for your application, you have to know exactly how the interface is affected. Because sometimes we think it is very nice, okay, it's working, but if you don't understand the interface, even solar cells. So people find the somebody already reported 19% efficiency, but our lab we do the same thing, but ours is only 10%. Why? So those are some of the challenges that we face because of the interface. Whether it is solar cells, whether it's CMOS devices, that actually can change. So this is actually I mentioned before this evolution of these things, and then the high mobility substrate. The strains actually current train we are somewhere around here. This is going to go to 3 nanometers. That is first step. They are thinking about that the transistor will go to 3 nanometers. Now this is actually as I mentioned before. This is actually scaling, and this is the functional diversity. So that's what actually going to happen. And in this process, this integration of germanium and 3.5 are actually coming out. So what is going to happen now, the way it looks like, the part of the chip is not the inside a single chip, you will have many transistors, so germanium transistor and 3.5 transistor. But you can say one part of one area of the chip will have the 3.5 materials, gallium arsenide circuits. So you have silicon CMOS and gallium arsenide bipolar transistors. That is actually going to happen very soon. Anyway, any questions on the interface? There's a break for tea. Let's see how much material I have. don't have much material. Okay, that's fine. Gym break. Okay, so we'll have gym break because this is a good point to start. So, any questions before you go? No questions.
So this interface that's get leakage currents are is the low frequency noise or high frequency?
Low frequency. Yeah. Interface states actually contribute significantly to the low flow. We'll talk about that thing this afternoon. Right? I put those things together. We had some experiment with using FinFETs also. We stress that to increase the defect density and see how it is changing. So we will discuss that.
Okay, so we friend, please have it and come back in 15 minutes.
Yeah, if you will be there, if you have the line. Yeah. Okay, so we'll, if this, for you. So the next generation trend is, for example, in the smartphones, we have a lot of processors in there. First of all, we have the signal processing chip, and we have video processors. We have many different processors in addition to the main microprocessor. So many different chips are there, but they are still packaged separately, even though they are flip chip packaged, but they are separate because the chip that communicates with the outside world, the bestest, that is not silicon, still, that is gallium arsenide, or Indian gallium arsenide, or Indian gallium arsenide, depending on the company, depending on the quality they have got. Now the trend is that can be integrated into the silicon base. So you can have one corner of the chip will be gallium arsenide chip. The rest of them will be silicon chip. So this is instead of two separate ones, it will be a single one. So but the problem is when you start those things, the biggest problem is the interface. So this is a big critical issue. The interfacial layer. So what we did, I mentioned about this germanium thing. Germanium native oxide has poor electrical properties, first of all, extremely unstable. And germanium diffusion into hafnium oxide. If you have hafnium oxide, germanium diffuses there. So that is actually a big problem. If you just normal processing like 300 degrees centigrade, you will find one hafnium germanate will form in the interface. And so this is that's why they want to surface passivation. So prior to hafnium oxide deposition, what you put on the germanium surface here, then you can have the germanium cannot diffuse. It cannot even germanium diffuses. Sometimes the oxide also, the oxygen comes in from hafnium oxide and forms an poor germanium GOX. So that actually is a problem. So then that is actually required. Then post-diffusion process condition and thermodynamics needs to be controlled. If you passivate this somehow, then do some annealing, then everything changes. So this is actually very critical. A couple of examples here. Sure, okay. Let's do this by nitridation. We treated these things nitrated first on the germanium substrate, and then deposited hafnium oxide. So what we expected that there is a possibility of this formation, GOX formation, or GOX and NY, some sort of things, a combination of that formation. And then another group, actually, we worked with them. We got these devices to take some measurements, and that what they did, they put some on the top of germanium, which is silicon, a few monolayers of silicon, and oxidize that silicon film to make silicon dioxide. And then deposited hafnium oxide on the top. So it is like this. You have, but they couldn't finish the entire silicon completely. So now there is a lot of band gap variation there. Because you have germanium, you have silicon, and then silicon dioxide and hafnium oxide. But they said that way we can actually get the germanium devices working, because we can still have the electron flow in the germanium channel. So this is actually another one. And this is this IMEC group, and we collaborate with IBM. We got samples from them. My student went there to make the devices and brought it back. So let's look at some of the characteristics. First of all, when we put, this is actually the initial sample without any nitrogen. Now once you nitrate the surface, then the hysteresis, that means you go this way and come back, hysteresis is actually reduced. But when you look at this as a function of frequency, there is a large frequency dispersions. So also in this side. So, and then if you look at the interface state density, the nitrated one has more interface state density. So it was very strange. We said, okay, we'll put nitrogen, but actually created more DIT in the band gap. So it was not acceptable sort of thing. So first of all, this frequency dispersion as well as interface state density. Because of, if you have frequency dispersion, then the leakage current goes up. That means it says that leakage current is there. Who contributed to the leakage current? The defects that went inside the high K layer that is there, plus the interface defects also contributed to the leakage current. And then we try to find out that, okay, why not we went for some low temperature measurement, change the device temperature, and look at what are the type of defects it forms. So we found out that this is the trap defect energy level in the band gap itself, germanium band. So we found 4 different ones. So some of them are actually shallow traps. This is sort of very shallow trap, 0.1 electron volt. But there was some of them. There is one of them will be little bit not exactly shallow because the germanium band gap is smaller than silicon, but you have some sort of defects that will be contributing to the leakage process. And then if you look at GEOX formation, if you have some GEOX formation, and then in the beginning in the interface with the germanium, and you have GeO2 formation if you want to do it that way, then also you have a lot of defects that comes in the GEOX. It's not a perfect dielectric. So then, and then again you stress these things. What you do, you stress and look at the inject charge into this. Okay. This one is plotted instead of function of time. Is plotted as an injected charge injector. So this is very simple in terms of looking at this. You have current and then multiply the time. Less charge, isn't it? So you can convert the time into charge depending on what is the leakage current. And then you see the flat band voltage shift. And then with non-nitrated, the flat band shift, the one which is no nitrite, no nitrogen, the flat band shift is minimum, whereas as a function of the injected charge. Whereas with the nitrogen, actually the flat band shift is worse. So these are some of the issues we saw. And then some cases actually, if you do this as a change in the interface state density as a function of stress, there is not much changes. Why this? Because I mentioned that if we inject like a silicon case, we'll inject electrons, then it comes there, then hydrogen diffuses through these things and creates effects. But if we interface, if we look at interface only, so this flat threshold voltage is combination of 2 charges. If metal is fixed, so only charge in the dielectric will contribute to the change in the threshold voltage. One is in the bulk charge defects created inside the high K layer, and one is at the interface. If the interface defects are created. So we looked at the interface defects. So interestingly, no change in the interface defects. So if you stress it a longer time, there's still no change. The reason behind that is in germanium, it's interesting, it's not the same as silicon. Because silicon has a dangling bond standing, and we put hydrogen to passivate. There is no dangling bonds in germanium. So what happened if you have some oxide forms there, let's say silicon GOX or whatever a GO2 form in the beginning? What happens to the dangling bond? That means the dangling bond energy that is sticking up in silicon that actually is inside the valence band. So we don't see them. So there is no way you can passivate them. So people try to do this type of passivation, but still didn't work.
This interface density states are
Pardon?
threshold voltage and threshold voltage.
Threshold voltage will affect the interface charge as well as the bulb charge. Because bulb charge will change your QSS. That's why threshold voltage will change. But it creates a bulb charge, but not the interface charge.
It will reduce the threshold voltage. Interface charge.
It reduce or increase, because that depends on the type of charge formation. You understand? Because if we have negative charge, it will actually increase. If you have positive charge, it will decrease. It's already doing so. So that's the way the flat band voltage will sit. So this is actually, if you look at the silicon structure, as I said, you have a dangling bond and you have silicon dioxide and hafnium oxide. But germanium system is actually this low ESR signal, actually no interfacial dangling bonds. And there is no germanium epicenter like we showed it to you for silicon. And then actually is also this dangling bonds is below the valence band. Whatever energy that contributes is not in the band gap of germanium, but inside the energy. So that's why you don't see. So hydrogen diffusion model that we used no longer valid for germanium. So it was only thing is some people are trying to find out if there is a hydrogen presence in the germanium crystal, that may come up. So maybe we'll talk about a little bit when the experiment we did talk about that thing tomorrow. So this is actually still work on progress. This work was done many years ago. Many people worked on this. But thing is, right now also there is no germanium devices. Only silicon germanium channel, some places, some devices they have introduced. There is no germanium devices. And if we go to another interesting thing is we did one experiment high K on gallium arsenide without any passivation. It was a very bad CP characteristics. So we thought, okay, maybe it is very bad for us. Maybe you are like you are doing some things and you say, oh, what I did, others are doing so nice results. Our lab is so bad. We don't get at those things. That is actually is always true. But what exactly is going on in your device or what other people are trying to do, you have to understand everything. It's not only at present. We tried to see the model, and this is titanium gold alloy. We have the gate material, and then looked at as a function of temperature, and the behavior of the interface was similar. But thing is, the interface defects were so bad, we had the CP curves was as a function of temperature was very, very bad. So this is high frequency CP curves of this as a function of temperature, large defect density, and the inversion capacitance decrease due to an increased time constant. Because of the, if you have a small time constant, then you have very bad the carrier capture time. This is actually carrier capture time. Then you have very poor characteristics. Then we looked at some other groups. They said, okay, if they have done nitrogen, they did some nitrogen incorporated layer in the interfacial layer with gallium arsenide. So their CV curves are very bad also. So I said, what happened to them? So I asked this guy in the conference, and they said, we don't get good devices. Then they realized that the interface defects are extremely high in gallium arsenide. This gallium arsenide is, if you have gallium-rich surface on the top, if you have gallium arsenide, you clean the surface. You may have gallium on the surface, or you have arsenide in the surface, arsenide atoms on the surface. Then you have completely different EIT. So this was not that easy. And then passivation technique, there is not many, nobody knew what is the passivation technique to make a MOS transistor in a gallium arsenide substrate. So the standard process that we followed for nitrogen passivation and all these things, that was what they. Now DIT was coming on the 10 to the 15. That is not acceptable at all, because in silicon dioxide is 10 to the 10. So it is not acceptable. And then people said, okay, sulfur passivation. Let's do some sulfur passivation. So sulfur has an energy very close to the gallium arsenide surface energy. So then they also found, look at the CV curve, doesn't look like CV curve, and all values are different. See, if you change the frequency, this is actually as a function of frequency. Your question was like that, isn't it? Why there is a, first of all, this doesn't flat, it's not flat, this is the accumulation capacitance. And also, it's all, doesn't look like a standard MOS CV curve. So, and this work is publishable, by the way. If you understand what is in there, you can publish this work. If you can model that in your simulation, you can calculate, model that because of the defect distribution inside this dielectric and interface, you will get curve like that. Then that is fantastic. People didn't understand. Even now, a lot of people do not know what exactly the solution. So then you can see if you have gallium arsenide and you have indium gallium arsenide, you will change different percentage. People are trying to do different percentage of these indium gallium arsenide samples so that they can adjust this interface and distribution of defects inside in the band gap. So that work was going on for some time, and this is sulfur pessimism. There is another thing also people said, okay, since all this sulfur and nitrogen are giving trouble, why not we put some silicon? The silicon we know very well. So they put some amorphous silicon, that is A silicon, at the interface, and then deposit hafnium oxide, like the standard process in the silicon. So that actually some people said, okay, maybe it's going to work, but it's very difficult to model those things because what happens when you have gallium, and then you put gallium arsenide, then you put silicon, then there is a huge band gap release, like a step things that you saw here. There will be a difference in band gap. So that actually will create some problems. So, but that improved the CV characteristics a little bit. So minimum thickness of silicon at the interface passivation layer, so needed to prevent the formula. The formula pinning, this is actually the result of formula pinning. And you can see this just the formula, this is the CV curve is a straight line. It doesn't look like CV, there's no accumulation to these things. They said that if you change this, put this silicon, amorphous silicon in the interface and deposit high K, then you are seeing the formula spelling is a little bit better. And then 1, 2, 3, 4 is all the frequencies and sort of things. That is actually also there is a huge frequency dispersion. And then these germanium interface. Some people put even germanium at the interface. And then as a germanium passivation, so they were trying to reduce the EOT. Germanium passivation led to ultra thin EOT. Okay, the EOT can go down with low dielectric leakage current. But again, the similar problem. This is not high quality devices. These are individual devices with good trying. Then Sematech group actually they have 11 nanometer process. They developed some devices. They put indium gallium arsenide with the 5347, and then deposit zirconium oxide, and then the aluminum oxide sort of whatever. Because aluminum oxide and found out, and indium gallium arsenide, the minimum interface states were created. To do anything else, that was a problem. And with aluminum oxide also will nucleate very well on gallium arsenide. Hafnium oxide was not. Let's say if you deposit hafnium oxide directly on gallium arsenide, it may not form. It may try when it ALD didn't form. So this is actually they tried, and they gave some good results came out. This is a group in San Diego, Hiroshi Wai from Tokyo Institute of Technology. See this frequency dispersion they found, and there was a huge change in the device. This is as a function of frequency. They did hafnium oxide with indium gallium arsenide, so the many different combinations, different layers. See, this layer of this indium gallium arsenide is not one layer. They have multiple layers to reduce the lattice mismatch, and then finally you end up one very thin indium gallium arsenide with this layer. Then you can do this. So that is actually, this is the dispersion devices. So Al2, so the aluminum oxide as a passivation layer, so also people put those things that improve the device properties level. Right now, that's why the moment you get some benefit in the gallium arsenide or indium gallium arsenide transistor, silicon, the industry is pushing it very hard, so they were very good devices came out. So it is still in the backward. Another thing also people did the gallium artemonide. Gallium artemonide has the mobility of bulk mobility of 77,000. So even though you can get a lot of degradation, you get 7,000, still it is very high speed device. So people are trying to do, this is the Penn State group. So they were trying to do this gallium arsenide and this adjusting the process conditions. So the process condition also is a big factor. How your device is fabricated. Any device, if you do like in titanium oxide or anything in the solar cell, if the process condition is slightly different. For example, we did some cadmium telluride solar cells. It's very simple. You just put thin films, and then on the top of the contact we put copper. But we annealed it in 200 degrees. And then you can see the copper was sitting all over. It went to cadmium telluride band gap. It went to cadmium sulfide band gap. So the device was dead, and that is because copper. So many things can happen if you change the temperature. And then there is a Takagi group in Japan. They found out if you can do with hafnium oxide, if you can do some several cycles for putting a hafnium oxide, aluminum oxide like this, then you can reduce the DIT level. But it is still between 10 to 12 and 10 to 15, the lowest possible DIT. So this dielectric deposition and the interface was a huge problem. So then impact of 3,5 deposition comparisons is MOCVD, MBE, and so this actually gave, this is actually another group they published in 2015, and that actually that if you do MBE, then you can make better devices. The thing is, MBE you cannot process 12-inch waves. MBE is still very small and very expensive technique. And those are still being used. Large MBE systems are used for 4-inch waves for LED deposition for the gallium nitride. So this DIT was also a little bit better, but it's still 10 to 12. This is actually 10 times 10 to 12, that is 10 to 13. So this is still up. It's nothing really final on that. Okay, there is a Sematic group. What they did, all the papers published until recently. Many different 3,5 material like gallium artemonide, gallium arsenide, different percentage of gallium, indium gallium arsenide, aluminum gallium arsenide. They found out the DIT values. The DIT values everywhere in the backend. So right now, sort of very few people are considering the 3,5 MOSFETs. So that's why this the scaling of silicon. If you are working on silicon, be happy. It will still continue on 3 nanometer, which will be another 15 years. So you will have good jobs in South gallium arsenide. You don't know where. The other thing also, if you look at the 1001 and 111 gallium arsenide, the distribution of in the defects and the energy levels in the interface states of gallium arsenide band gap is that actually decides the formula voltage. So that is actually very critical when you have some interfacial layer, and that decides the formula voltage. And that due to missing. So if you have one arsenic atom missing, and one gallium ion is atom is missing from the surface, you will have formula voltage. So those are some of the scientific ones. So for this type of devices, you need to have surface chemistry, and then surface orientation of the substrate. What plane, crystal plane you have, position of the electrically active defects on the band gap, what sort of thing, because this will change if you go for aluminum gallium arsenide or indium gallium arsenide. This distribution will change. How that will change, and what process condition you do, whether you want to do it with LD and following the rapid thermal annealing, that will also change. And obviously, if you implement any passification technique like nitration or sulfur, or whatever. So this actually brings in again the at this point the blind man looking for an elephant, identifying an elephant. The same situation. First of all, what sort of interface specification you do? Aluminum oxide, silicon, germanium, hydrogen, nitrogen, sulfur, and then you see what are the dielectric deposition. You are going for the cyclic deposition of DATA, deposition anneal, or deposition this thing as deposited. What sort of thermal budget, what temperatures you will be depositing. They are trying to reduce below 200 degree, but it was very difficult now, but that is actually another issue. And whether you go for plasma enhanced LED or just ALD, sorry, plasma enhanced ALD or just ALD. And then comes channel material. When you look at channel material, high-K germanium, aluminum oxide, gallium antimonides, or aluminum oxide in gas, or gallium arsenide, or lanthanum oxide, hafnium oxide, multi-stack. So these are some of these people have reported in this area, these structures. Another things came up, since we have this type of problem, why not we go for the buried channel? That means you can have, you design the channel in such a way, the electron transit will not be at the interface working through this. So if you can adjust this band gap variation, then you can move the channel to below the interface. So that's called buried channel. You know that we tried in silicon also, buried channel. And then if you go for buried channel structure, maybe you will be better off. Now, how to create FinFETs using gallium arsenide or germanium? That is also not that simple. Obviously, going to there is, I think, one paper that came out in nanoware Indian gallium arsenide, but doesn't meet any real specifications. So then high-K graphene interface. You can people are talking about high-K graphene. It is aluminum oxide also does nucleate on the top of graphene. That is a big problem. So they deposit a layer, a monolayer aluminum on the top of graphene before depositing high-K. So graphene, in my opinion, graphene transistors are not going to happen. Because you cannot make the 12-inch graphene processing using graphene transistors manufacturing. The same way carbon nanotube, when it came up, first carbon nanotube transistors, with IBM declared that they have carbon nanotube transistors. My feeling was, we have discussed on in this conference, that we said, okay, you cannot manufacture the way we manufacture silicon devices. And if we cannot manufacture that way using carbon nanotubes, then the industry will not be interested. We can academic, we can do a lot of research and put one transistor working, but industry will not be interested. Same thing happened for, you might have heard many years ago, you were not born that time, the high temperature superconductor material came up. That is high. So high temperature superconductor material at room temperature, typically the superconducting material work in very low temperatures. They could have the Cooper pairs working in room temperatures. And then everybody was, when it was declared, everybody was jumping. Now we'll have super fast trains, elevated trains. We'll have chips, fantastic chips will be working. But what happened? Those materials are not manufacturing molecules. You can create those materials as one, several molecules, but they are not stable. You cannot manufacture. There is no way. So the high tissue superconductor, actually there was huge amount of money spent to make devices, make real things in there. So it's all disappeared. Same thing happened now in US. If you write a proposal for funding on carbon nanotube, with anything, sort of almost anything, you will not get it. Nobody will fund your research. Because carbon nanotube is sort of gone. Some people are trying to introduce those things in organic solar cells to enhance the efficiencies, but those are the things you have to look at. So that is the area of research that you pursue. the big chunk which was came 2 years ago only, 2D semiconductors, is still excellent for applications. The 2D semiconductors, people still try to understand the concept of it, whether it's modeling and whether it is making the devices out of it, still there. But there is no funding now because it was very difficult to make 2D semiconductor transistors for manufacturing. That means it will be very difficult to manufacture. So this is what actually the story is. So I will, I think that's the way, that's much I have for this morning. And if you have any questions, we can discuss now. Any questions at all? We have the tea break, too late. They're all awake, but there's no material. Okay, another thing also, there are some questions about the modeling. So the idea is there are a lot of modeling papers because you don't have facility, experimental facility. So a lot of modeling papers are comes out in the journals and publications. If you look at carefully those modeling work, they are already supported by some experimental work. So when you develop your basis for a model, let's say if you are doing a MOS capacitor with a new material, or something that you want to propose, have different metals and different gradations in the channel. But the thing is, you got to have a starting point where you have to understand all the parameters that can be affected. Sometimes for the initial device, you may get some default parameters by the tool providers. Go to, let's say, Synopsys or Silvaco, they provide some initial values or initial parameters, the interface state density. But when you make a new device, your interface state density will be quite different. So you should also know how to incorporate those values in your models. Who has used SPICE as a simulation tool? Anybody in the class, in the group? Anybody use SPICE for circuit simulation? Okay. You have used SPICE? When you use SPICE, what tools did you use? Which company has SPICE?
Cadence Spectre.
Dylan?
Spectre.
Spectre, that analog simulation. Okay. Do you know what models they use? Like device parameters are being used, so that's why you got a nice curve. What models they have used? Because that actually, when you do the device, you select a particular technology. What technology was it?
Silicon vSync. MOS 11.
No, MOS 11 and vSync models. But what technology is that? 0.18 micron technology? 180. What is the threshold voltage in that one? You don't know. Why you don't know? Where is it hiding? That one is hiding something. That those models are hiding. So the thing is, sometimes we do not understand what parameters they have used. What is the difference between the, let's say, the Cadence Spectre analog simulator compared to HSPICE? Have you heard about HSPICE? The Synopsys tool has HSPICE. Okay. What is the difference between that? So the idea is HSPICE, you can get those models, state-of-the-art models, or even 7 nanometer transistor, they have models, experimental results. What they do, they make, let's say, go to 65 nanometer or 45 nanometer technology. They make the devices, extract the parameters from a test set of device. And then they make circuits and then compare them. Then they release those values for simulators. Those who really like to do the simulation. And with the models, which will calculate the quantum mechanical effect, which will calculate different parameters. If you look at those model files, they are available in the internet. They have around something 50 different parameters. Okay. And they are exact measured parameters. And that fits into model. Some cases they modify the model to simplify in computations. And those are actually also, for that particular technology, they have decided what are those variables. Let's say this saturation current is lambda, use what is this VNC aux time VGS minus VD square, and then 1 plus lambda BDS, isn't it? So that lambda is different for different transistor sizes. So if you see the model, you will have lambda 1, lambda 2, lambda 3. Depending on the size, you use that lambda. It will automatically use the tools automatically use. If you don't understand that and run the simulation, you don't know what it is you are getting. Okay, so I want you to, even if you have to do the modeling, I want you to always know what is in there, what calculates your values that you get. Otherwise, you may be giving some wrong inputs. Let's say you are creating an input file, circuit some wrong input, maybe you get fantastic output. But that's useless, isn't it? So understand that thing. And if you start from scratch to create a device, you got to introduce the values or look at a baseline. Baseline is whatever is already available in the simplest device or the most advanced device that is already fabricated, and those parameters are available. You modify your parameters to match with that experimental result. Those are published by somebody else. Once you have that, then you have a baseline. That means you have that much defect density, that much parameter variation, that much the voltages you can work. Those values are already available to you. Then when you do the simulation, and then you can, from that point, you go to advanced concepts. Let's say you want to propose a new device which nobody has thought about. Then you have a baseline ready. Then you propose a new device, a new device design, or some whatever this thing. Let's say some people try multiple metals on the gate to speed up the transit time, to have the reduce the transit time. So you can do all those things, or the threshold variation across the channel. But if you do not have the baseline, everything is wrong. So those are actually very important concept in modeling. And then you calculate back and see if we change that, what are the things that are actually happening from your baseline. And many times I see some papers come from review from India, and they have no idea what they're doing. They say, okay, we use Synopsys tools, and this simulation, this is the result. I mean, they have good new device, but nobody knows whether that device will work or not. That paper will not be accepted unless you come up with some ideas first, explain your model with the existing experimental one. Then you go to the next level, proposing a new device. That is sort of the concept of simulation. Because simulation, always remember, garbage in, garbage out. You may be a fantastic tool. You do not know what is the input, the output is junk. If you know the input, do not know the models, the output is junk. And people will figure it out just like that. And what type of models? There are a lot of things you can do with those tools. But there are very good models there, very good equations are there, very advanced devices, their equations are there. But for the new device that you want to do, first develop the basic. Same thing also, and many people came to my class saying, oh, they have used SPICE, but they didn't know what is the threshold voltage. They picked up some transistor, put them together, did the simulation, it worked. They have no idea, but even you send it for fabrication, making a chip, nothing will work. Because every technology is different parameters. If you design something in 0.18 micron technology which is available to you, now somebody wants to send it 0.065 or 65 nanometers, it will not work. But they have a different model, different equations, everything. So there is another set also to look at in SPICE model. They have level 49, level 53. Those are actually the labels decide the set of equations used in those, and they are available in the internet. It's not like you don't know what are those equations. Even SPICE manual will have description of those equations and reference to those papers. BSync model, there are also reference why BSync model is introduced and what it does. So those things you have to understand if you want to do any type of simulations. And what are the models used? Because Synopsys also makes their models available to that these are the equations used for these devices. You can do many things. So those are some of the things I can suggest that you look into very carefully what to expect. Any questions? No questions? Okay, so let's meet at 2 o'clock today. So let's meet every day at 2 o'clock. Is it okay? You can have lunch and come back by 2?